Welcome. If we could come on in and find a seat, it is time to get going, and I do not want to cheat any of our speakers today. And if my co-conveners would come up and join me. Welcome to the union session on celebrating 50 years of scientific ocean drilling, how the past informs the future. I'm Jim Wright. I'm the chair of the United States Advisory Committee to IODP. My co-conveners today, two of them are with me. Leanne Armand from Australian National University. She is the program scientist for ANZIC, Australian and New Zealand IODP Consortium. And Tony Morris, who comes from the University of Plymouth. And he is the chair of ESAC, which is great for IODP because it has an acronym within the acronym, the ECORD Science Support and Advisory Committee. And Yoshi Tatsumi was unable to come. He's the fourth of the co-conveners, and he's from JDESC, the Japan Drilling Earth Science Consortium. Whew. That was the hardest part of this introduction. I've been asked to remind you, if you have a comment or a question of any of the speakers, please use the mic in the center. This session is being recorded. A couple of other quick announcements. I draw your attention to the Tyra Prize this year. Brandon Dugan is the recipient, and he'll be talking Wednesday afternoon at 2:40. The IODP Town Hall is Wednesday evening at 7 in the Grand Ballroom at the Washington Plaza Hotel. This spring, Anthony Coppers is putting together a special edition in oceanography. It's coming out in March of 2019, and it is Scientific Ocean Drilling, Looking into the Future. We will be sitting down in the front row because you can't see anything from this perspective, and we want to enjoy the talks as well. But I'd like to introduce our first speaker today. It's Susan Humphreys from Woods Hole Oceanographic Institution. She's a senior research scientist there. She is an expert in hydrothermal systems and looking at how the water-rock interactions influence the geochemistry. I think you can control here.
Okay. Can you find my presentation?
Why am I not driving? Sorry.
It's all right.
Okay, now does anybody see the cursor? There we go.
Okay, well, thank you very much, and good morning, everybody. It's a pleasure to be here to celebrate the 50th anniversary of scientific ocean drilling. And I've been asked by the conveners to provide some sort of historical perspective this morning on the program. As you know, we've had ocean drilling has been a major capability that has helped us advance a number of our understanding of a number of different processes. I'm going to briefly talk. Oh, lights.
Do I control those? Is there anybody in the back who can bring the lights down?
Okay, I'll keep going, but hopefully we can do something about the lights. I'm going to briefly talk about Project Mohole, which was the precursor to much of the scientific ocean drilling. And then we've had a series of 4 other programs since 1968 that have provided the scientific community with that capability. Scientific ocean drilling dates back more than 60 years to Project Mohole, which was suggested by Walter Munk and Harry Hess in 1957 and was proposed to the National Science Foundation by the somewhat famously named and somewhat self-organized American Miscellaneous Society. The The NSF actually funded the phase 1. It was going to be a 3-phase drilling project to drill using the Global Marine CUS-1 that also had 4 outboard motors attached to it to create a dynamic positioning system. And this was the first dynamic positioned drilling vessel in the world, and the system was actually designed by Willard Bascom. The crews managed to drill about 170 meters through sediment and into the questionable layer 2, which obviously proved in this case to be basalt. Unfortunately, due to issues related to increasing cost estimates to continue the program faded away after that initial phase. However, it did accomplish some very important things. First of all, it recovered the first samples of basaltic ocean crust. Secondly, it demonstrated the feasibility of deep-sea drilling and the feasibility of dynamic positioning. And there was a huge amount of public interest in the project because the famous novelist John Steinbeck participated in that cruise and wrote an article in Life magazine. And it even inspired a telegram from John Kennedy that you can see on the right there. So it obviously received a lot of attention. Sometime in the mid-60s, 4 of the directors of the major oceanographic institutions got together and realized how important it was to be able to have a program to collect continuous records of sediments in the ocean. And in around 1964 or 5, I don't remember the exact date, they signed a memorandum creating the Joint Oceanographic Institution's Deep Earth Sampling Program, the name of which later changed a little bit, that came together and ultimately resulted in the deep sea drilling project. That project was initially funded by the National Science Foundation, and Scripps Institution of Oceanography operated and also participated in managing the construction of the Glomar Challenger. That program became more international as more international countries, as well as US institutions, joined JOIDES and DSDP and created what became known as the international phase of ocean drilling. And that from that point on, the program has always been international. DSDP was very successful. It sailed 96 legs and drilled 624 sites, most of which were exploratory in nature. Now, things were a little bit different on the Glomar Challenger. You can see in the top left that human roughnecks actually manually handled the drill pipe on the rig floor. And of course, today we have a tool that is called the iron roughneck to do that. You can see the uniform of the science techs on the catwalk was a little different. It appeared to be shorts and flip-flops with t-shirts optional. And women were few and far between in those days. In the bottom left, that's a picture of one of the only 3 chief scientists during DSDP who were women. That is Margaret Linen on leg 92. And in the bottom right, you can see a young, newly minted PhD on her first cruise on leg 54, in which I was the only female member of the scientific party. There were a lot of highlights to DSDP. It was a new capability. It was doing really wonderful things. I can't go through them all today. I've just listed 4 for you there. Importantly, it enabled the development of the field of paleoceanography. And we are all aware of how important that field has become over the course of scientific ocean drilling. In terms of technical highlights, a deep water re-entry capability was developed that allowed us to re-enter holes, and hydraulic piston coring was developed for soft and semi-lithified sediments. And it was first used on leg 64, and of course has become one of the major tools that we use for paleoceanographic work. Perhaps the most famous result of DSDP occurred on leg 3, which was the verification of the concept of seafloor spreading. Here you can see the two co-chiefs, Art Maxwell and Dick von Herzen. And on that cruise, they collected and dated basal sediments in a transect across the South Atlantic Ocean and demonstrated a correlation between basal sediment age and distance from the ridge axis. Another important contribution was the fact that it was determined that the deep basins of the Mediterranean had thick evaporite deposits that were formed during the Messinian salinity crisis during a restriction of circulation in the Mediterranean. And this was a concept that the community found very difficult to accept. And I have here a quote from the initial reports for that leg. And Ken Shu wrote, and I'm quoting, "The idea that an ocean basin the size of the Mediterranean could actually dry up and leave behind a big hole thousands of meters below worldwide sea level seems preposterous indeed. We recall that our colleagues were vehement in their negative reactions. The idea was thought to be physically impossible." Once DSDP ended, the program, scientific ocean drilling, tended to shift a little bit in its emphasis. There was more of an emphasis on thematic planning in response to community-driven proposals. Prior to this, most of the planning for DSDP had been done within the JOIDES advisory structure. And secondly, continuous coring and downhole measurements became routine. The ocean drilling program was the first, the successor to the deep sea drilling program. It was dominantly funded by NSF, but with significant contributions from 22 international collaborators. The program was operated, or the ship was operated by Texas A&M, and a new ship was brought into the program, a commercial vessel that was leased, the Sedco BP 471, that got renamed the JOIDES Resolution. This program was extremely successful. It provided 18 years of ocean drilling to the community, and it sailed 110 legs and drilled 650 sites. In the around the mid-1990s, there was a real movement among the scientific community to see if we could develop greater international funding that would give access to more capabilities for ocean drilling. And the sort of plan that was envisioned was some sort of commingled funded program that would include a ship to be supplied by the Japanese that was ultimately the Chikyu, which was a riser drilling ship. The JOIDES Resolution would be upgraded significantly, and then the European Consortium for Ocean Research Drilling, ECORD, would provide mission-specific platforms for places that were unsuitable for the big drill ships, such as high latitudes and also shallow water. That program came to fruition, and it was a program with a complex arrangement involving commingled funds and a central management organization that was overseeing the operations of the program. That program sailed 52 expeditions. It faced some challenges. The first one was there were delays in the construction of Chikyu, and there were also delays in the refitting of the JOIDES Resolution. The other challenge it faced was funding. The drill ships and the mission-specific platform operating costs turned out to be greater than the financial resources available. And so the whole original concept of year-round operations of 2 drill ships and 1 mission-specific platform cruise a year could not be met. Nevertheless, this program contributed significantly to the science in a number of fields, as you will see in a minute. Both ODP and IODP were guided by science plans. These basically with the community writing drilling-related proposals addressing scientific priorities that were developed by intermittent international workshops. The ocean drilling program had 2 major themes and a number of sub-themes, dynamics of Earth's environment and dynamics of Earth's interior. And in those days, the inclusion of biological and microbiological studies was very, very limited in the program. And in fact, the biosphere studies were a sub-theme under Dynamics of Earth's Environment. As we transitioned into the integrated ocean drilling program, that theme became its own, and a new theme was created, the deep biosphere and the subsea floor ocean. I'm not going to go into the scientific highlights. They're numerous from ODP and the first IODP. My purpose in showing you these lists, and they're not exhaustive in any way, is to really illustrate the breadth of topics that this program has contributed to. Within Earth's environment, the long historical records that have been collected through sediment coring have helped really define the long-term history of both climate change and global sea level on a variety of temporal and spatial scales. In Earth's interior, drilling of crustal sections and mantle sections have established the fact that fast and slow spread crust have different structures. There have been studies that started to illuminate fault zone behavior at active plate boundaries, where, as we know, Earth's largest earthquakes occur. And the development of the cork, which was a method of placing instrumentation down a sealed hole, really revolutionized the way we were able to think about how we could study these things because it provided a monitoring capability. And within the theme deep biosphere and surface ocean, the drilling program provided the evidence that there are microbial communities within both the sediment and the oceanic crust. They've placed limits on placed constraints on the limits of life, and there have been the development of a number of hydrogeological and microbiological experimentation in different environments that have really contributed to understanding the subsea floor ocean. The International Ocean Discovery Program, notice it's the same acronym, different name, was the follow-on program that started in 2013. And this was a program that has really tried to bring stronger links between Earth and life sciences, and a program that has tried to bring in new scientific ideas and capabilities with a major focus on societally important problems. The funding model has been simplified. Now each of the platform operators, Japan, US, and ECORD, provide their own facilities and run their own facilities. However, the scientific planning for the drilling program is still centralized and actually does the planning for all of the cruises in terms of the ranking of scientific proposals. It is still an international program. It still maintains the access to the 3 different types of platform and to the core repositories. It still is and will be a rigorously peer-reviewed, driven from the bottom type of operation with a flexibility to respond to new ideas. And of course, many of you in this room have also had the experience of spending 2 months at sea on these ships. Within the new program, IODP, there are 4 themes and 14 challenges. I'm not going to go through all of them. The first 3 derive in a way and follow on from the original IODP. The addition of the 4th theme, Earth in Motion, is a reflection of our ability now to think about processes and hazards on human timescales because we have the capabilities to do make downhole observatories and do monitoring of events. And that has become a very important part of IODP. The JOIDES resolution during the course of the new program is expected to circumnavigate the globe. Just as a few examples, in the first 5 years, there has been a large program looking at initiation of subduction in the Izu Bonin Mariana Arc. There was a concerted campaign of expeditions looking at monsoons and regional precipitation around India. And most recently, the ship has been working around Australia and New Zealand on a variety of topics. The CHICU is continuing to work on nantrices at the Nankai seismogenic zone. And the mission-specific platforms have done some spectacular expeditions, including the Chicxulub impact crater drilling, and also looking at the relation between serpentinization and life. And as you can see from the track of the JOIDES resolution and some of the other dots there for the CHICU and mission-specific platform, we can look forward to more exciting science in the years to come. I talked about international participation, and the program has really benefited from the ideas and the expertise of the participation of a number of international countries and consortia. Ken Shu, shown in the bottom right, was the first international co-chief on DSDP leg 13, and over the course of the program, there have been international co-chiefs have made up about 43% of the co-chiefs. In terms of women, these are the 3 women that were chief scientists during DSDP. The situation has improved considerably in the current program, International Ocean Discovery Program. Women make up about 1/3 of the co-chiefs. And in the bottom left there, you see a graph of the percentage of women participants throughout the history of scientific ocean drilling. You can see a number of blips down to 0, quite a lot in the beginning. But as you can see, there has been a steady rise in participation of women. And if you look specifically at graduate students in the current program, they make up almost half of the graduate student community. So that's significant progress indeed. And while we're talking about education, education and outreach has become increasingly important throughout scientific ocean drilling. It has always trained the next generation of scientists, and there are many in this room, including myself, who have benefited greatly from participating and being involved in the scientific ocean drilling community. And that's a really important legacy of the program. Over time, the education and outreach effort have continued to broaden, and today it includes undergraduates, K through 12, and informal education venues. And today, educators sail on the ships and create opportunities for the students and the public to learn, often in real time, about what's going on out on the ship. And so in many ways, the arms of scientific ocean drilling have broadened to include the larger public community. The scientific ocean drilling has advanced many areas of scientific endeavor. And these series of scientific highlight volumes basically present many of those major accomplishments. And coming soon, as was stated earlier, there will be a special edition of oceanography that will be coming out that is called Scientific Ocean Drilling, Looking to the Future, and that will be out in March. Oops, sorry. The other important thing that we should think about is, as we get near 2023, is the successor program. And I think it's fair to say that scientific ocean drilling has been one of the most successful, long-standing international science programs that we have seen. As we move towards 2023, there are already planning activities underway to prepare for the next program and to prepare to provide new opportunities for scientists around the world to participate and further their science. And with that, I thank you all very much, and I'm going to leave up an ad for a new video about the history of Antarctic drilling that you can see at the IODP booth or you can see on YouTube. So thank you very much.
you, Susan. Do we have any questions? Just one brief question, if any? No? Okay. Thank you, Susan.
Thank you.
I'd like to introduce now Professor Richard Arculus. He is an Emeritus Professor at the Australian National University in Canberra, Australia. He obtained his BSc and PhD at Durham University in UK in the 1970 and 73 respectively, and followed on with postdocs and academic positions in the US until his move to Australia in the early 1990s. Richard's expertise and research in geochemistry, igneous and metamorphic petrology and volcanology has taken him around the world and often on research vessels such as the Geordie's Resolution. Indeed, Richard has been instrumental in re-establishing and maintaining Australian and New Zealand's membership in IODP since the integrated phase. He will be speaking to you today on the theme Earth in Motion, which I have no doubt will thoroughly cover the highlights of IODP over the last 50 years, and will be as entertaining, if not more so, than his appearances in the Expedition 351 Flash Mob YouTube video, if you've ever seen that. So, ladies and gentlemen, I will welcome Richard Arculus to the podium, and I have to get his talk up first, perhaps.
Can we still try and get the lights?
Oh, and I have to point out we cannot dim the lights because of the recording. That's what we've been told, so I'm afraid you'll have to put up with bright lights.
It's on the max, isn't it? It's on the big one. Yeah, presentations, there you go. Another one down there.
Getting that. Got it?
Super. Max, all good. Good morning, everybody, and thanks for the invitation to inflict this on you all. And I would also like to say that I don't have a photograph of myself in 1968. If I did, you'd see I should sue this program because I used to be 7 foot tall with a lot of hair. This is a career damage. But I also wanted to acknowledge the enormous technical expertise and skills of the people that run the ships and the drilling program and the whole community that's conspired to get together to execute this astonishing program and its results. My mission today was to tell you about the Earth in Motion theme of the present science plan, and I'm going to basically present you with a series of adverts for expeditions that have been achieved, completed in the last few years, not in any sense a comprehensive coverage of any one of them or all of them, but just to tell you a few hints about where you might go to look and dig all the information out for yourself if any of this interests you. So yes, there's the processes and hazards on a human timescale. Some of the things that are going to be covered I have stuck in because Michibayashi-san decided he would not present this, and I've been intimately involved in this particular part of the recent drilling campaigns, subduction initiation. I do, courtesy of the recently completed expedition at Brothers, also thrown in a few tantalizing slides. All the science is under embargo, but I will show you some wreckage that they managed to achieve with some of the equipment pulling it out the hole. Which is the advance. Oh, here we down arrow, thank you. Nothing happening. Mac keyboard, good point. Here's the science plan that the program is presently operating under, and one of those, in terms of hazards and the Earth in Motion, is featured at the bottom right. Personal reminiscence in a moment. The Earth in Motion had these challenges, as you can see. I'm not going to read them out to you, but basically to become societally relevant, given the capabilities of the drilling platforms, can we do things that matter to people? I often tell my undergraduates, you want a career in science, promise to make them money, economic geology, they'll all be rich beyond their dreams, or threaten them with death. And this kind of slide you can see shows you that the great hazards that we face globally, especially around the Pacific Rim and around subduction zones, are particularly significant for societies. This is the team. I was a member of this dirty dozen that were charged with writing the science plan. There were several meetings. There are some faces that keep being reborn in different guises, and around those tables are some of the characters that are present in this room and have been very active in the programs in the past. I did want to mention this. In terms of global geochemical cycles, inputs, outputs, leftovers to the mantle, this is one of the places the Earth churns itself from the exterior of the planet into the interior. But the cartoon is basically an advert in terms of discovering how these convergent margins first get initiated. There are several places in the world where we could all go and have a look at a new divergent margin being created. Convergent margins generally bury themselves, and drilling is really the key way to find out how does this start? How do you start a new subduction zone with the consequences for global Earth geodynamics and geochemical recycling? In terms of going out and doing some observations, one of the world's great theoretical physicists, I think this is a wonderful quote, said, "You can sit in your ass thinking about the way it might work, but until you actually measure it, you won't know." He was, of course, a particular friend of Michael Faraday. Faraday was the great experimentalist, and Maxwell was the guy who put it all together. In terms of practical experimentation, Stephen Hales was the first guy to measure the blood pressure in an organism. Presumably he asked somebody if he could borrow his horse, tie it down and stick a glass tube into its main arterial vein and measured the rise to which the blood rose. We do these sort of kind of things these days with the drilling program. It's particularly interested in fluids and how they move through the exterior of the Earth. Scientific drilling has enabled the first sub-seafloor observatory systems to be established. Sue mentioned those. It's been in the last few years, in particular, illuminating fault zone behavior, especially the enormous earthquakes that have occurred in the last decade or so. And it's also realized that there are flows of fluids through all parts of the seafloor, from ridges, back arc systems, through to fore-arc prisms, and of course, the arcs themselves. This is a cartoon drawn by Becker and Davies, or it's clearly a tidied up version perhaps, so they're back of the napkin kind of representation. But this has become realized. We can now permanently monitor fluid processes and pressures in downhole boreholes. So of course the horse example, that was a transient. You wouldn't want to leave the tube stuck in the horse for any length of time, and we can do this with the ocean floor. I have a personal background in tracing fluids through the Earth's crust in terms of dying streams and looking at flows of fluids through cave systems. In the case of the ocean drilling program, we've been using sulfur hexafluoride, a variety of fluorescein, to monitor flows of fluids in the ocean crust. The corks that have been placed down these boreholes can be instrumented and in real times also transmit signals back to base, and also revisited by submersibles and tapped for their information. These are not cheap instruments to deploy, but they have been remarkably successful in the last few years in doing exactly the kind of experiments one could hope, both active and passive, in the ocean crust. For example, Expedition 301, so we're going back to one of the predecessor programs, but 301 and 327, looked at flows of fluids in the Juan de Fuca Ridge off the west coast of North America, injecting and monitoring flows of fluids between various wells. And that was successfully achieved. For example, here is an injection site, and the flows of sulfur hexafluoride monitored with the outlets of the various other sites could be quantified, and in detail, the fluxes through the ocean crust measured. This is a direct representation experimentally of what theoretically might have been derived, but it's always good to have some proof of how these things work. In the last few years, the concept of slow slip earthquakes in particular, but also the general earthquake distribution, the seismogenic zones, transition zones, and general slippage on the major thrust faults at subduction zones have been examined closely. This paper here by Damien Safer and Harold Tobin was published in the Annual Reviews of Earth and Planetary Sciences a few years ago, but the cartoon is from their paper and represents the various kinds of relative motions and fluid flows in these convergent margin major thrust faults. Now in 2004, an enormous earthquake, as you're all aware, occurred off northwest Sumatra, caused an immense amount of damage, one of the largest quakes in the last 100 years, major tsunami sweeping across the Indian Ocean. This was the kind of wreckage caused by the tsunami in northwest Sumatra at Banda Aceh. And subsequent to that, an immense amount of modeling and analysis of what happened and why has taken place. For example, Thornley and others in 2005 published a paper in Science. The drilling program has visited this site of the earthquake generation and explored in detail the nature of the incoming plate. And the bottom seismic section is showing you the sedimentary package which has come down from the big river systems draining the Himalayas and into the Andaman Sea and northwest Sumatra. And the results of that have showed some very interesting results. For example, that first of all, the rupture extended much closer to the trench than expected. There was extensive dehydration, dewatering basically of hydrous silica in the sediments by the loading pre-subduction. And it's not clear that that is duplicated elsewhere in the world. So one of the messages from this is that not all great earthquakes are triggered in the same way or confined to the same sedimentary package. Now, that's perhaps distressing in the sense of we'd like to know that there's some universal truth about what's going to cause big earthquakes where, but that's not the case, as I'll show you in a moment with respect to northern Honshu. But there are other margins which behave the same way as the Sumatran margin, for example, in Makran, the Southern Lesser Antilles, and Cascadia. So the lessons learned from this drilling off Sumatra will no doubt be extended to some of these other margins. I was going to turn briefly to Nantraces, the drilling of the accretionary prism off the southern coast of Honshu and Shikoku. This has been historically a major source of major seismic events. It's been a major effort by the Japanese community, led by the Japanese community in particular, to understand how this works, of huge societal relevance, not just to Japan, but to other nations in the world. The various holes have been designed to look at the inputs, the behavior of the accretionary prism itself, and currently the ship is back out on Expedition 358, drilling through to one of the major thrust faults of this accretionary prism, a major goal that's been underlying a lot of the program of investigation at this margin. So the present expedition is attempting to drill right down through to one of these thrust faults. It's out there now. It's already extended down multiple kilometers below the seafloor and is aiming to be 5 to 8 kilometers by the end of the expedition next March. This margin in particular is of interest because it was one of the first margins where the low-frequency tremor and slow slip events were recognized, events that pass unnoticeably to any human being, but are now, of course, well monitored around the world. This is a cartoon on the right from the JAMSTEC website, the offsets coming down to the current drilling, Expedition 358, and here's the thrust fault target at 8 kilometers or so depth. Best wishes to the team. In 2011, another enormous earthquake struck northeastern Japan, the so-called Tohoku earthquake. A major tsunami, as you know, probably was generated. The interesting aspect of this particular zone was the major slip that generated the huge earthquake and tsunami was preceded by a slow slip event. And this now seems to be the case in a number of earthquakes. Again, as I'll show you with respect to the New Zealand margin. The Japanese were able to, within the required dissipation of heat on the thrust fault, before that had dissipated, managed to get back to the site and penetrate in great ocean depth and into the fault that had broken. And paper published by Kirkpatrick et al. And Tectonics, the major points I think that they make is that the rupture was localized in a smectite-rich pelagic clay, so not like the Sumatran margin. There was both distributed and local deformation around that thrust fault zone, and there appears to be two modes of behavior: the low strain rate fabrics that are generated during slow slips, and the high strain rate, which are generating faults. Beautiful images and recovery were obtained by JFAST, and all of that is in the various scientific publications that have emerged since the drilling took place. I want to turn just briefly to the slow slip recognition. And one of the first observations took place in 1979 by Kanamori and Stewart. And this was along the South Honshu margin. Low-frequency tremor, of course, is also associated with volcanic activity, movement of magma in pipes. But away from volcanoes, it's now become apparent that many subduction zones, in fact, have low-frequency events which can occur around considerable movement along the various thrust faults. Quite why there sometimes is slow slip and sometimes rapid slip is yet to be completely understood, but it's clear margins experience both kinds. And as I said, just recently, there's been a paper here's one by Wallace et al., published in Nature Geoscience, to do with a triggering by a major slip of a whole series of slow slip events elsewhere along the New Zealand margin. For example, a couple of years ago, there was a rapid slip here down at Kaikoura at the northeastern end of the South Island of New Zealand, and the effect could be monitored on this Hikurangi margin to the northeast. So this rapid slip triggered a whole series of slow slip events along the Hikurangi margin. Slow slip events have occurred independently of a trigger by a major rapid slip. Recently, the program has been visiting successfully this margin in 2 expeditions. The sites are shown here on this diagram, and 2 expeditions, one of which was logging while drilling, Expedition 372, and more recently, observatories established and core recovery achieved at these various sites across this active margin. We are blessed with the fact core recovery has been achieved, but also the observatories are in place to monitor very closely what's happening to this margin. Major seismic surveys have been completed, which would allow deep penetration by drilling into the various thrust faults that accompanying the activity on the northeast margin of New Zealand. Now, I do want to turn, as I said, briefly to subduction initiation, key part of the global theory of plate tectonics. I was involved with a campaign of 3 expeditions that targeted the northern part of the Izu-Bonin system in 2014. One of these, Expedition 350, was in the rear arc and examined the evolution of the rear arc system, but 2 of them were targeting what happened when this subduction zone was first initiated. The Expedition 351 was just to the rear of this remnant arc, the Kyushu Palo Ridge, which was abandoned by back arc spreading in the Shikoku Basin, the Paresi Vela Basin, about 25 million years ago. The volcanism continued in what is now the active volcanic arc, but the Expedition 351 targeted the basement upon which the first arc was built. Now, conceptually, I guess that the message I want to give here, when people talk about an arc, they think it's a chain of Fuji-like volcanoes. What we know now is those isolated stratovolcanoes located 100 kilometers above the downgoing slab, that's not the way the arc starts. The arc, if you looked at it, when you were first there when it was happening, would look like a set of seafloor spreading. There was no isolated volcanoes, it was just a massive collection of isolated rift zones, maybe short length, but dominated by basaltic volcanism. That basaltic volcanism is really, in many ways, indistinguishable from mid-ocean ridge basalt activity, and we know now there are many examples of that in the geological past, which represented the inception of subduction, not a chain of Fuji-like stratovolcanoes. 352 drilled in the forearc around the type location of the arcane, weird magma type called Boninite here at Chichijima. By the way, George H. W. Bush was fished out of the ocean close to the island of Chichijima. So the 41st president owed his, I guess, future life to the fact that a submarine was nearby and managed to retrieve him from the ocean. Now I'm going to show you a cartoon. It is a cartoon. Life is always more difficult than a cartoon, even though there are some fundamental truths in this kind of diagram. It's from a paper by Bob Stern, published in EP, Earth and Planetary Science Letters, and basically there are 2 types of subduction zone system, starting them, either induced, because something else happens somewhere else on the planet and forces a subduction zone, or, as I'll show you in a moment, spontaneous. Here's some examples of how do you induce a subduction zone, like colliding an incoming continent or oceanic plateau and transferring the subduction zone outboard of lump B, or polarity reversal. For example, here's the Ontong Java Plateau coming in on the Pacific Plate and triggering a subduction polarity change as a result of the unsubductibility of that thick oceanic plateau. In terms of spontaneous subduction, we think this more or less applies to the Izu-Bonin case, but with some modifications, as I'll show you in a moment. But basically, although this says spontaneous, there is a degree of induction going on here, that around 50 million years ago, a change in the Pacific Plate motion triggered some changes in subduction systems from New Zealand to Japan at around 50 million years ago. And the drill sites, Expedition 351 and 352, were here straddling the new arc. That's not true, really. That's not supposed. What you got was not a red Fuji volcano, but initially all this light blue stuff was the new oceanic crust created in the initial stages of arc magma generation. And here's the combination: induced, spontaneous. Where's the type example? Western Pacific. Where else might you find it? Currently at the Puisaga margin south of New Zealand. And there's a lot of interest in tackling that because it could well be the initial stages of a new subduction zone system. 50 million years ago, Pacific Plate, transform fault next to a package of old arcs, and here's the new subduction zone system starting because the direction of the Pacific Plate motion changed, perhaps as a result of the swallowing of the Izanagi Pacific Ridge. And the two drill sites for the expeditions, 351 and 352, the kind of magma types are recovered, but we have a really good knowledge as a result of the investment of IODP in targeting the critical issue of subduction initiation, at least in the Western Pacific. Briefly, I want to mention Chicks Club as a target. This was an immensely successful mission run by the Europeans, but of course with international participation. The world's only known peak ring, which was materials of which were recovered during the drilling. Some cartoons of what happens when you smack the Earth with a 10-kilometer diameter asteroid. It would have been a fairly stimulating place to be on the Yucatan at the time this happened. And of course, the leg was entirely successful in nearly 100% recovery of the smacked up rock that is generated as a result of an energetic impact of this type. Astonishing looking rocks, granites that are like sugar grains, pulverized, and of course large melt sheets that were generated at the time. I also wanted to mention Expedition 366 on the current phase of the program that has drilled in the serpentinite seamounts that intrude the forearc of the Mariana system. And the interesting aspect of this particular style of activity in convergent margins is the serpentinite seamounts that appear and have class of material that are coming up from the subducted plate. In fact, the first time a subducted carbonate sediment has been recovered from the downgoing plate and transported up to the surface in one of these seamounts, as well as blue schist. If you don't believe blue schists are formed in subduction zones, the stuff going in here is not blue schist, but there are lumps of blue schist coming out of volcanoes. So it demonstrates what we think we always knew, that that's where you generate these high-pressure, low-temperature metamorphic rocks. Wonderful recoveries of materials from the drilling. This is not your ideal drilling site because the material is horrible and the technology for getting this stuff out is just remarkable that anything can be retrieved. And I've also threatened you with an advert for the Brothers 376. So none of this, Cornell, relax, is confidential. These are cartoons that accompanied the various proposals to drill in this system. In terms of adventurous expeditionary, this really comes close to the limit. You could propose that we want to target these systems, magma driving hydrothermal circulation in the crust above, all kinds of things going on in these systems. We know now that what goes on at the major hydrothermal centers at the ridges also takes place at back arc basins, and in a different kind of way at the chain of submarine volcanoes in the arc systems of the world. Expedition 376 targeted the Brothers volcano. By the way, these volcanoes, there are a lot of submarine volcanoes. They're named either after Maori gods or heroes or dead professors. So there are people who've had things named after them in this chain, but perhaps it's just an indication it's time they got off their profession and went and did something else. The beautiful imagery of the Brothers volcanoes, a central cone and a caldera. And the wondrous thing about this site is there are magma volatile, rich systems in the cone site and dominantly seawater recirculated sites on the caldera walls. So you get two for the price of one. Classic, if you've not seen these kind of images and you thought these hydrothermal chimneys are only associated with the mid-ocean ridges, classic chimneys, black smokers, white smokers. This, as I said, the crustal wall sites, crustal fluid rich and magmatic gas rich on the cones. Wonderful recovery. This expedition set a new record for amount and length of recovery of rocks from the feeder systems of these hydrothermal vents. And they also achieved a nice result with damage to the drill pipe. This is what you get when you stick it into hot water and corrosive acids. So here are my conclusions. We have, over the past few years, made dramatic advances in the technology and capabilities. We're looking at active processes, monitoring and experimentation. And of course, we have, I believe, made major progress in satisfying the aims of the science plan currently. And we're only halfway through. There's plenty more to come. And Sue put up one of these diagrams. This is the expeditionary plan for the next few years. Many exciting things that are going to come out of the Earth in Motion theme. Thanks very much for your attention.
Thanks, Richard. I think we've got time for one quick question, if there is one from the floor. Looks like you're escaping, Richard. Thank you very much. You need to come round this way. Let's just swap over here. Okay, it's my pleasure to introduce Katsuo Mitsubayashi to you. He's a professor at Nagoya University and uses microstructural analysis to understand the structure and rheology of the oceanic crust and mantle. It's been one of the key players in driving forward the planning for eventually drilling to the Moho and into the mantle by deep drilling. But has been involved in the Oman drilling project, an ICDP project, which has sort of a unique scenario of collecting cores from the Oman ophiolite and then measuring them on board the Chikyu while it was docked in sorry about that. Let's stop that. Now we know what happens if you overrun your time. So taking the cores to the Chikyu and analysing them there. And there's been an Oman DP session being run this morning concurrently with this session, unfortunately. So Katsuo-san also gets the sort of honour of being one of the very few people in AGU to have given 2 talks in 2 different sessions inside 1 hour on the same day. And so I'll hand over to you. Thank you very much. You need to use the down arrow here to change.
So, thank you very much. And I'm Katsuo Mitsubayashi. I'm from Nagoya University, Japan. And I also must thank to Yoshi Tatsumi, who is a Japanese giant, who asked me to present today. Anyway, let's start. And I'd like to talk about Earth connections in IODP, which are deeply related to mantle drilling project, which is I'm one of the proponents right now. Okay. Oh, sorry. So, to congratulate to the IODP to 50 years of the time. Yeah, but for Earth connection, particularly since I'm involved in mantle drilling project, I'd like to emphasize here again the Project Mohole, because this is the truly origin of our project. So, and the origin of the Earth connection, indeed. Then, phase 1, Project Mohole, has been proposed by Walter Monk. This is back to 2016. He's still in good shape. I was so pleased to see him have a lunch in his house. It's really honored. Then, anyway, this Project Mohole, actually, at phase 1, and going to some challenging site is in 1961, April. Then they penetrate 183 meters, then gets through the sediment and gets 14 meters of basalt. This is very important because this is the first evidence for seismic layer 2. Now it is quite, everybody knows, seismic layer 2 is basalt, but it is Project Mohole who revealed this first evidence. However, it was terminated in some reason in 1966. Then after that, of course, IODP started in 50 years. Then during these 50 years, there are so many places has been made some holes. Then that was a great achievement indeed. And I was so happy to be one of involved in this fantastic project right now. Then earth connections. Earth connection must be the hard rock drilling. In fact, this is truly hard rock drilling. It's going to be quite slow, not so easy, in fact. So they have a challenge, 4 challenges. Thank you very much for Professor Arculus to present some, this lower part of the challenge. And in this my talk, I like to concentrate these 2 challenges because this is related to mantle drilling project. So ocean drilling toward mantle drilling. And then here, I'd like to show you some current status and future plan. So among the enormous holes, this is compiled by Benoit Ildefonse of France. Hole drilled in ocean crust more than 100 meters below sea floor in 50 years. Only, in fact, 38 holes by 25 crews. This is the reality in earth connections. Then, not only this, when we see how deep they drilled, most of them are less than 200 meters. And some are going to more than 1,000 meters, but very few. So hard rock drilling is truly hard drilling. Then, challenge 8, what are the composition, structure, and dynamics of Earth's upper mantle? Then this is a view by a geophysicist. Geophysicists never seen the reality, but they often draw these huge schematic diagram. In fact, we geologists is very ashamed to draw up this kind of schematic diagram because we know how complex it is. Then, so we do what we have done. So yet we do not know exactly what is that uppermost mantle. So that's why this challenge is still, we have. So to achieve this, of course, geophysicists help us. That is a seismic survey. We need seismic survey anyway. So this is actually a seismic reflection image done by Jamstek and Kodaira-san et al. We have very beautiful Pacific Ocean seismic reflections. We see beautiful Mohorovičić discontinuity, that's Moho. Then with this Moho, we define the clustered mantle is here, something like this. So another part, crust mantle, like this. So very limited part, but we always rely on this seismic survey. Then someone compiled like this is a global Moho depth. Then you see, this is actually depth is depends on the color. So blue is the shallower and red is the thicker. So you see the oceans have a quite blue, quite similar among different oceans. In contrast to the depths in the continent, this part is very thick, but some part is quite shallow. But compared to that, ocean is quite blue, quite shallow, almost everywhere, uniformly. Then, long time ago, geologists who studied ophiolite, such as the Oman ophiolite, actually. They suppose that ocean cluster section, that is the famous as called the Penrose model. So from ophiolite, we see the sediment and the pyrolavate and the sheeted dike complex, then layered gabbro, then the lowermost crust. Then after that, more deeply, it is the uppermost mantle. So this section is geologists actually propose this must be the oceanic crust section. Then it works with with the seismic velocity structure in Pacific Ocean. So it seems to be pretty consistent each other. So, oh wow, that is great, things. However, as I told you, only 38 falls by 25 crews in last 50 years. With this result, let's compare with the result. So this is the reality. This is that 38 falls. This is 2,000 meters in this level. Then this enlargement is here. You see, particularly this part this blue is a gabbro, and green is a serpentinite peridotite. It's such a very shallow level. It should be the pilolava or sediment in this depth. However, these gabbro or serpentinite peridotite must be occur in the much more deeper section. So this trick is come from slow spreading ridge. Always slow spreading ridge, they found gabbro or serpentinite peridotite. Even when drilled deeply, they found very thick gabbro with no shallower section, volcanic sections. Then, in contrast, in fast spreading ridge, it's somehow quite similar to this model. So, anyway, seafloor exploration has demonstrated that oceanic crust is not uniformly layered everywhere. Some part is quite consistent, some part is not at all. This is the reality. So, various lithological sections in ocean question, what is the crustal architecture? So this is a Penrose model, style model. Then this is the other model. These are, in fact, come from the different oceans. Penrose model seems to be well fit to Pacific Ocean, but it's questioned because we know only shallow level. Then Atlantic Ocean and Indian Ocean, and also Arctic Ocean too recently. Although they only drilled very shallow level, still they found very deeply sheeted rocks. So that's why they make such looks very complicated section. But we must think about this section. Then note that moho depths are quite similar among oceans, as you see this fruit, although their crustal structure vary. Then, what is the moho? Still this question stays. Then there are two classic models for the relationship between the crust mantle boundary and the moho. One is the Penrose model proposed by geologists. In this model, crust mantle boundary is equal to moho, so 6 kilometers. The another one is a famous Hess model in the original. Crust mantle boundary is much more shallower. The moho actually is the boundary between the serpentinite and the fresh peridotite. And this is the two end members. There, you can think about much more variation in the section, whatever you want, in fact. Then, two challenge. In fact, these two challenges are deeply related to each other. Because until we understand what is the oceanic crust, we never understand what is the moho, and we never understand what is the uppermost mantle. Even what is the definition of the crust mantle boundary. The very much still question remains. Then, although Project Moho has terminated, they couldn't make a platform to reach to the moho mantle, but now we have a platform. That is the Chikyu. With this, after 50 years, we have a Chikyu with this fantastic platform. We are now trying to reach to the moho. Then we got a new moho project. It is not very new, but moho project has been updated to be moho to mantle. It's called now. We say M2M. That is the 2012. So they submitted in 2012. The 7 lead proponents, and including myself. Then at that time 60 co-proponents. But I believe it expands more people, much more now want to go to the moho now. Then M2M. M2M is somewhere in the Pacific Ocean. Try to drill the 6 kilometers to reach the moho. So journey to the Earth's mantle. It's much far longer way than that road to the moon, because moon we already reached to the moon, but still 6 kilometers is a very, very long way. So at the moment, three selected regions in M2M. Among this, Hawaiian North Arch, first site survey has been done, 2017. Now you can see this result in the Ohira et al. 2018 papers. But other two sites is not planned yet. So it is still a long, long way to make it happen. That is the reality too. Then I'd like to emphasize what's the significance of the hard rock drilling. Hard rock drilling science is a link between the ocean floor science and seismology. Ocean floor science, this is a scale to 1 millimeter, 1 meter, 1 kilometer, 1,000 kilometers. So ocean floor science would be something like this. Then we survey in the surface, and not accessible in the deep. Then seismology. Seismology is a much more longer scale than we see from the waves to the deep section. Among these two, hard rock drilling science is the between. So we see the true rocks and also we see the deep. So it actually connects. That is the link between the geology and the seismology. With this diagram, where is the mantle drilling project? Here. Mantle drilling project is almost in the field of the seismology. This is a truly link between the seismic global scale material science and seismology. So we need this project. And one more. Moreover, mantle drilling is not only for earth science, but it must also be for planetary science. So now, the American reached to the Bennu, asteroid belt. Japanese already reached to the Ryugu. This is studying the formation of the solar system. Then, for all melting in the formation of the Earth, then at the present, that we have a layering, nice layering, then ocean crust, they become arc and the continent, and this become a nice global cycling here. Then, mantle drilling project, where is we here? Here. Mantle drilling project actually is searching for the origin, what's going on the global cycle. So this another importance. How far can we understand the evolution of this planet without mantle drilling? What do you think? Besides, hard rock drilling related to mantle drilling will reveal the actual life of oceanic plate. So oceanic plate is a birth in the mid-ocean ridge, then going toward to the convergent region, then matured, then hydration along fault. So our drilling project actually reveal all of these processes. Then, finally, the road to the mantle drilling. Last 2 years, including this year, we did Oman drilling project. At the moment, the session is going on. So I'd like to briefly show you the result of Oman, some activity of the Oman drilling project. Last year, on Chikyu, 14 countries to then 63 scientists gathered. Then this year, 24 countries from the 87 scientists gathered on Chikyu. Then all very studying the Oman cores, more than 3,000 kilometers of cores. So this is the crust mantle boundary. You see, this is a CT image, only scanned by Chikyu. And this is the cluster section. So mantle section starts this blue line here. So this is in the Oman core on the crust mantle boundary. So we finally obtained crust mantle boundary cores, but we'd like to have this core in 6 kilometers below seafloor. Then, with the CT data, we see the three-dimensional fabric. So this will help our future mantle drilling project. So we have completed to drill 3,200 kilometers of monophyolite, and it's going on. And we have now special issue on JGR. It is open. You will see our achievement in few years. Something like this. So this is Oman. And then, so Oman project is hard rock analysis on drilling vessel Chikyu. Then we are planning Godzilla Megamurion drilling. So this is the hard rock shallow depth drilling, not deep, shallow depth drilling. The next, slow-mo, led by Henry Dick. This is the hard rock intermediate depth drilling. Okay. Then next, outer rise drilling. This is the pretty hard drilling. Hard, chart is very hard. So this is also challenging for us. Then FOAC mantle drilling. This is a deep water depth hard rock drilling. No plan yet, in fact. This is it's a planning, but not scheduled at all. But after this, eventually, we try to reach to the through Moho in the Pacific Ocean. So this is the final message. Hard rock drilling, that is Earth connection in IODP, is now in active mode after 50 years since the end of the Mohol project. Thank you very much.
We do have time for a question or a comment. Clive.
That's a very exciting talk.
Thank you.
On a very exciting project. If you give us an idea of, given you've got the platform.
Yes.
How long will it take that platform to drill into the Moho once you find a site?
How long what do you mean, the time?
Time.
Or when it start?
When is it? No. How long will it take Chikyu to drill 6 kilometers through basalt?
You mean how long? When?
No.
How
many years?
Will it take
How
2
many
years? Will it take 3 years? Will it take 6 months?
It depends on the. If we just keep drilling, then maybe 1 year. If everything going so well. But this is the reality. Then it's better to make a hole first. Then because we have a technology to get some wall rock later. Also, Chikyu have the cuttings, which we can also analyze. But personally, it's nice to have a nice mass of rocks.
You want the core, as do I. Thank you.
Yes, you're welcome.
We still have time for another question or comment. Thank you very much.
Thank you.
You want to drive? Wrong one? Yeah, here we press escape.
Oh, you can all read what I'm going to say.
Oh, what do you? No, this one right here.
So look, see that it's got the presenter view up there.
Well, that's what you asked for.
Yeah. There. Got it.
I'm there.
Good. I think we're there.
Back
oh,
up.
but no.
I got to introduce you.
Okay.
Just a quick word. If Jamie Austin were up here, he would note the diversity and gender, the diversity and the international participation, I look out and I see at least 6 or 7 different colored ribbons to go around. This truly is a program that crosses many different specialties and scientific interest. And as I look out, it's a very colorful group. And I see blue ribbons sitting with orange ribbons. And so this is a good thing that we discuss many different aspects of scientific disciplines. Mo Ramo is not hard to introduce. She has been involved with ocean drilling science in many facets, and she was a co-chief. She was one of Susan's statistics of leg 162, not expedition. And you're a co-chief on an upcoming expedition, and the number escapes me at this time. But she'll be going out as another co-chief. She is the Bruce C. Heesen Lamont Research Professor at Lamont Doherty Earth Observatory. She is the curator of the core repository, and if you haven't been there in a few years, it is a very active scientific and research facility. It is moved into the 21st century, and a lot of dynamic research going on in cores there in the Lamont repository. Mo was asked to talk about what we've learned in the last 50 years about our climate system, and I'll hand it over to Mo.
Thanks, Jim. So how do I advance, right here?
Probably down.
Down, okay.
And you have the...
Great. So thank you so much for inviting me to be here and talk about the drilling program, which has probably been the single most important influence on my career. I've been involved in the drilling program for 35 years. And when I was asked to give this talk, thinking, oh boy, 50 years, ocean climate highlights. Well, I mean, you just couldn't possibly do that in 20 minutes. I mean, I feel like I can say with utter confidence that we know more about Earth's climate history because of the drilling program and because of the people involved in the drilling program than through any other scientific endeavor, through any other instruments, through any other disciplines. So, and Susan referred to some of those achievements in her talk. So I thought rather than just kind of go through this list of all the amazing stuff we have learned through the ocean drilling program, I would reflect a little bit on some of the other really important contributions that I think the drilling program has done that we should be incredibly proud of, how it's impacted my life a little bit, and also what I think is one of the most outstanding scientific problems that still remains in all of Earth science, and that I think the ocean drilling program is the organization that's going to ultimately solve that problem. And that question is, how does the long-term carbon cycle operate? I still don't think we have a full view of that. So when I think about, if I had to say one word that described the ocean drilling program, to me that would be connections. And first and foremost, it would be all the connections of all the people that are involved. And I was talking with Carl Brenner. We were trying to estimate how many people had sailed out on the ocean drill ships for 2 months at a time at sea, 2 months at a time at sea, over 50 years. And we estimated that it might have been 6,000 to 7,000 people have sailed out at sea. And many of those people are in this room, and you understand the incredible connections you make with your colleagues when you share a scientific experience like that. And it's led to this incredible richness of interdisciplinary exploration and discovery that we all see. That this previous talks were all amazing, and I think we all see that and feel that. So also what's been truly amazing is that those people that have been involved in the program come from all over the world. And a lot of the greens are washed out here, but publications from results from drilling expeditions have come from 98 countries. We all know how hard it is to monitor downstream results of expeditions and experiments, so this is probably a very conservative estimate of the contributions that the ocean drilling program has made over the years. And just reflecting personally on the impact it's had on my life in 35 years. I started as a shore-based scientist as a graduate student. I just went through my CV and pulled off all the little things off my CV, and I know that there's so many people in the room that could put up lists almost identical to this, and I know that because I look out and I see so many people I have been on committees and in workshops with over the years, and think about all the science that we have done. But one thing that I really want to point out here is the picture in the upper right. That's me having my first beer after 2 months at sea in Reykjavik. I'm in my early 30s. I was co-chief. I wasn't the youngest co-chief, nor was I the first woman co-chief, as we saw earlier. But at the time, I truly understood what an extraordinary opportunity I was being given. And Delia Obo and I had written a proposal to drill sediment drifts in the North Atlantic as postdocs. And just a few years later, we were out there doing that. And, you know, as the women in the room at least know, the early 90s was like a different world. And so, you know, there were lots of mixed messages about whether you should even be scientist. And so I truly appreciated how incredible that opportunity was. And I'll just like to say, here's the map again. If there is any young person in this room that thinks they can't do that, I would say you are not giving yourself enough credit. You guys should be thinking right now, teaming up with your partners, your colleagues, your graduate student friends, your fellow postdocs. The boat is now scheduling cruises in 2022, 2023. That's not that far off. Propose science. It can happen. These are not things that get done by a committee up the top. It's all community driven. So I am deeply grateful for those opportunities. When I think back how what we know about climate has changed in the 35 years I've been involved. When I started grad school, the picture at the top, that's Site 552, Nick Shackleton had just published that long record that suggested that the northern hemisphere ice ages started right around 2.5 million years. Very low resolution record. It had some significant hiatuses, unconformities in it of a few 100,000 years, and these were because of the drilling techniques at the time. And here's where I want to really emphasize the amazing contributions to science of the technological developments that have happened over the years by people like Keir Becker. And in this particular case, I'd like to shout out to Bill Rudiman, who basically established and demonstrated the technique of multiple hole drilling in the construction of composite depth sections. So now we have continuous, beautiful records. Here's the last 5.5 million years. This is a composite of 50 such long records. They're probably now close to maybe 80 or so. Just as a plug, if you want a nice poster-sized version of this for the wall of your seminar room, this version can be downloaded on my website. If I think about the longer history of climate, what do we know? Here's what we knew when I started grad school, Douglas and Woodruff. We were just beginning to see from benthic oxygen isotopes that global cooling began around 40 to 50 million years ago. Our ocean drilling around the same time was showing the first records of IRD off of Antarctica. Now, what do we know? This is very typical of where the state of the art of where we are now. We have incredible records of the Cenozoic climate change. And this is just Stello 18, but of course we have C13 records. We have all kinds of proxy records from which we are inferring climate physics, chemistry, dynamics. And it's very exciting. And of course, one of the most amazing things, here's Jim Zakos' curve showing, again, the global cooling since the Eocene. But what we've also saw, coming along a bit later, certainly by the 2000s, we are able to reconstruct atmospheric CO2 through time and show that indeed the global cooling of the late Cenozoic was associated with a drop in atmospheric CO2, inferred through these proxies. So, why is CO2 decreasing in climate cooling through the Cenozoic? And I would say that the modern era discussion of carbon cycle behavior began with two papers, again about the same time, Walker et al. 1981 and Berner et al. 1983, and the Berner et al. Paper is affectionately referred to as the Blagg paper and the Blagg hypothesis. And through these sets of papers, which basically proposed that the entire climate system on the Earth's surface is essentially driven by seafloor spreading, where you have the input of CO2 through mantle degassing and seafloor spreading. That CO2 increases as it increases in the atmosphere. The greenhouse gases increase. The greenhouse gas increase. The climate warms up, and that CO2 is removed from the atmosphere through weathering of igneous, metamorphic, and carbonate rocks on the Earth's surface. If seafloor spreading rates doubled, atmospheric CO2 would double, climate would get warmer, and the chemical weathering rates of rocks would increase accordingly. And so this entire idea was based on the fact that there's a temperature control on weathering that acts as a negative feedback on excursions of CO2 in the atmosphere. Okay? So, and this was, this was the new paradigm of how we understood climate to work on long time scales. So here's a figure from that paper just to try to make that point again. Here's two estimates of seafloor spreading rates and the amount of CO2 put into the atmosphere through spreading rates. At that time, they were believed to be much higher in the Cretaceous. As spreading rates fall, atmospheric CO2 falls. As atmospheric CO2 falls, temperatures on Earth's surface fall. So according to the Blagg model, then, there's two things that it would make two predictions. One is that chemical weathering rates were highest in the Cretaceous when CO2 and mantle degassing was highest and temperatures were highest, with chemical weathering rates on the surface being lower at the end of the Cenozoic. And it also would make the prediction, obviously, that climate was cooling most rapidly when when spreading rates were falling most dramatically. And of course, we know that, in fact, climate was cooling much later. So this was a problem in my mind after thinking about this for years in the 80s, like why couldn't figure out why the cooling happened after the Eocene. And of course, this led, not to belabor it, to a paper that I wrote with my colleagues at Lamont, Bill Rudiman and Flip Froelich, saying that maybe Cenozoic mountain building was the actual influence on chemical weathering rates, and that there was a dramatic increase in chemical weathering due to uplift of mountains, that this drew down CO2. And of course, we know the collision of India with Asia started about the same time as the global cooling. And just to jump ahead, if you're a geochemist as opposed to a carbon cycle modeler, and you keep looking at the data, the least astonishing interpretation of all the proxy records that to this day come out from ocean geochemistry is that the flux of strontium, lithium, calcium is increasing towards the present. That's the most straightforward interpretation of all these geochemical proxy records. You can do some mental gymnastics and find other explanations, but to this day, geochemists trying to interpret the proxy signals that have derived from all these IODP records generally reach the conclusion that there has to have been an increasing flux of dissolved material from land over the Cenozoic. And here's a recent CCD compilation, which also is consistent with that. So that paper initiated this debate: what controls chemical weathering rates at the Earth's surface? Is it mechanical erosion, mountains and glaciers, or is it mean Earth's surface temperature, including papers that involve hydrology scaling with temperature? And these are two very different views of how the carbon cycle works. And in particular, you can look at geochemical proxy records. You can also, there's a whole subdiscipline of people that go out in the field and look at the modern situation today, right? And this is just a compilation. I wouldn't say every single person has come to the same conclusion, but I would say the majority of people that go out and look at chemical weathering rate in the field show a strong positive relationship between mechanical weathering rate and mechanical erosion and chemical weathering. The creation of surface area is a key feature in promoting chemical weathering rates at the Earth's surface, which consume atmospheric CO2. So this is a problem. So if mechanical weathering rates, which is what you see when you're out in the modern world, exerting the strongest control on chemical weathering, and you see that in terms of the rivers and their dissolved chemical loads where they're highest, if that's true, and this is consistent with geochemical proxy records over the Cenozoic, the question becomes, where does the large amount of CO2 needed to accomplish these inferred increases in chemical weathering rates on land come from? And this question has been very difficult because, as many of us appreciate, the size of the ocean atmosphere carbon reservoir is actually very small relative to the size of these chemical weathering fluxes and these fluxes going in and out. And there's really, if you want to learn more about this, there's two nice papers that were written early on, one by Eric Sundquist, another by Bob Berner and Ken Caldera. And here's one figure that just makes the point that if you take pre-industrial CO2 levels and just increase the chemical weathering rates by 25% and keep the mantle degassing constant, within 1 million years, you've removed all the CO2 from the atmosphere. And so obviously we know that didn't happen. So this is why we know that the inputs and outputs of carbon to the ocean atmosphere system have to be balanced on timescales of about 1 million years. And therefore, you have to have a negative feedback that somehow functionally knows what atmospheric CO2 or climate or related ocean chemistry is doing so it can act as a negative feedback, okay? And that's why the BLAG model was so intuitively pleasing. I mean, it says it's a temperature weathering feedback. But I still stand by my personal view, which is that it makes perfect logical sense, but it doesn't, there's not a strong canon of data that supports that that's what's actually happening. So the problem gets even worse. And that is because in addition to silicate weathering, which consumes CO2, the burial of organic matter on the Earth's surface also consumes CO2. There's been, I proposed once that CO2, that organic carbon cycle could act as a negative feedback, but I think much of the data since then has shown the opposite, that in fact on land, the uplift of mountain ranges and what happens in mountain ranges actually probably works to bury more organic carbon than oxidize more organic carbon. And again, people like Franz Lenore and Lou Derry have proposed that the uplift of the Himalayas caused global cooling through the burial of organic carbon. But the key point here is that it just makes the carbon budget problem worse, right? When you have something like the Tethyan orogeny happening. So where is all this carbon coming from? So I'm going to just end with 2 slides, and one is new ideas and old ideas made new again. I'm very happy with there being many more mysteries to solve, and I think they are out there, and I think we saw a lot of hints in the earlier talks about what you don't know about the carbon cycle. First is that we've known for a long time that there's probably precipitation of silicate minerals on the seafloor via reverse weathering. This is a topic we know very little about, but a topic which is also starting to reveal its secrets through ocean drilling. And I just threw up a few references up there. People in John Higgins' lab at Princeton are doing some really neat work. And again, the point I want to make is there are large fluxes of carbon involved here that are not currently in our carbon cycle models. Second, dissolution of seafloor basalt and basalt weathering. This is also, we learned that vast amounts, it's estimated now that the entire volume of the ocean circulates through these off-ridge hydrothermal systems every few 100,000 years. And we now know that those systems are doing reactions with carbon. So we need to know more about that. And again, this is ocean drilling work that's happening now thanks to the development of new technologies like quarks that are allowing us to study these systems. And then finally, the deep biosphere. This may be, as we just heard, one of the largest ecosystems on our planet. We know very little about the subseafloor geochemical processes that are going on, and they affect ocean chemistry, and they affect the global carbon cycle, and they may or may not be able to be sensitive to ocean chemistry and climate and act as a positive or negative feedback. And I just want to, I think I have a minute, I just want to show a beautiful example. I think this is such a cool paper where talks about the dissolution of seafloor basalt. And if you have warm bottom water penetrating through these off-ridge hydrothermal systems, it's dissolving basalt, precipitating carbonate, and removing CO2 from the ocean. And you can imagine as the climate cools, bottom water cools, you have less total basalt dissolution in these huge hydrothermal systems. You have decreased carbonate precipitation, and therefore more CO2 is left in the ocean. That is a functional carbon cycle negative feedback. And we have no idea how large it is and how sensitive it is. And so I'm really excited about what's left to discover in the deep ocean, and I truly believe we don't have a full unified understanding of the global carbon cycle and how it operates on long timescales. And I'm really excited about the work that I see a lot of the young people doing nowadays. So with that, thank you, and happy birthday, ocean drilling.
Time for questions, comments? Remember the town hall Wednesday night, tire prize Wednesday afternoon, and we'd like the speakers to come up and get a picture of you guys celebrating the birthday 50 years ago in July. Thank you all.